All right, guys, what I'm going to do right now is start a demonstration of what a Zoom lesson will be like, along with how we'll interact as far as what whiteboard is concerned. I'm not going to be looking at the camera too much because the camera is at the top of my screen, and my screen is really large, and I'll be looking down most of the time. So you'll just have to be used to that. I got my boom mic, as I told you in class. And so what I'm going to do in order to kind of get this Zoom demo going is do a recap of Gibbs Free Energy. The last thing that we talked about was Gibbs Free Energy. And so what I'll do is I'll use my iPad. Hello, iPad. And I'll use that as the primary. I'll use that as the primary mode of screen sharing, or excuse me, mode of delivery. So what I'll do is I'll start with where we left off, or at least with that topic that we were working on. And the first thing that I'll do then is share my screen, and you can hopefully then see the things that I'm seeing on Zoom. So now you should see my screen. And this is where we'll start. So the first thing that we talked about was enthalpy. And enthalpy is symbolized with H. And if we talked about a reaction, then really what we would be talking about would be a change in enthalpy, a delta H. And remember that a delta H will be whatever the final enthalpy is minus whatever the initial enthalpy is. And when you think about final and initial in chemical reactions, that means products are final and reactants are initial. Okay, so there was two types of enthalpy that we wanted to talk about. The case where reactants are higher energy than products. This is an energy graph. And the case where reactants are lower energy than products. This is an energy graph. In this case, we called it exothermic. In this case, we call it endothermic. And so one of the things that we need to be able to do in organic chemistry is decide whether or not a reaction is exothermic or endothermic just by looking at it. Now, one of the things that we did was talk about bond energies, and we talked about homolytic bond cleavage. So if I take H2 and I break it up into two hydrogen atoms, then this would be a bond dissociation energy. And at the end of the day, it always takes energy to break bonds. That should be sort of a common sense application of chemistry. Bonds hold two atoms together. If you break them apart, it takes energy to do that. Otherwise, if it didn't take energy, they wouldn't form bonds, right? They would just fall apart. Now, we did talk about bond dissociation energies. We looked at the chart, and we used bond dissociation energies to estimate delta H's. What I want to do is I want to skip through that, because in organic chemistry, we're not really going to be looking at the bond dissociation energies to estimate exothermic versus endothermic reactions. But you certainly can look at them. And so one of the things that we want to do, though, is to be able to figure out exothermic versus endothermic reactions by looking at them. And one of the things that we can do is we can usually get a handle on whether or not a reaction is endothermic or exothermic by looking at the different bonds that are formed. In this reaction, we have 1, 2, 3, 4 sigma bonds and 3 pi bonds. That's on the reactant side. And on the product side, we have 1, 2, 3, 4, 5, 6 sigma bonds and 1 pi bond. And if we think about this in terms of a reaction diagram, if we just remember the fact that pi bonds have more energy than sigma bonds, in other words, pi bonds are less stable than sigma bonds, then we will realize that we can calculate, or not calculate, but estimate the sign of delta H, whether or not it is exothermic or endothermic, just by that idea. So remember when we say unstable, we really do mean higher in energy. So if this is higher and this is lower, same would be true here. But in this case, we would say, well, what do we have? Do we have more high things or more low things? Well, on the reactant side, we have more high things than we do on the product side. So that means that in a very basic, qualitative sort of way, we could say that the reactants are higher energy than the products. And by that way, we can say the products are lower energy than the reactants. And that means we can draw this particular graph, and we can say that this is an exothermic reaction. And remember, since we're talking about delta H, which is H final minus H initial, we know that in this case, this is the high value, this is the low value, and at the end of the day, then this will be a negative number. And so this is the primary way that we'll use to sort of gauge whether or not a reaction is endothermic or exothermic, just by looking at it, right? We're really just going to look at the number of pi bonds versus the number of sigma bonds. And in this course, this is really all you're going to have to be able to do. Now, of course, if I ran the reaction in reverse, you'd have the situation where the reactants would be lower energy than the products. In this case, it would be endothermic. And that would be delta H low minus I messed that up. So I'm going to record this. I'm going to let it slide. This is low minus high. This is high minus low. And so let's recap, right? Small number minus big number equals negative number. Big number minus low number equals positive number. Now we got that sorted out. So if you had been confused just a little while ago, got you all cleared up now. And hopefully we got that sorted out. Okay, so that's enthalpy in a nutshell. And so now the next thing that we need to do is to think about this other piece, entropy. And I'm going to show you in a second, while both entropy and enthalpy are important pieces of deciding whether or not a reaction will go forward, we got to kind of dig deep into finding out what each one of them is all about. Entropy is essentially a measure of disorder. This is a common and most popular definition. Another definition, this is the one that I prefer, is that enthalpy is a measure of the number of degrees of freedom. Now, right now you're sitting around at home because you got the coronavirus, you can't go outside, your numbers of degrees of freedom have been limited, so you're lower in entropy. That's a joke. And so another way to think about it is the number of ways to distribute energy in a system, right? And distribute energy means particles, right? Because if you remember old Einstein, he said E equals mc squared. That means that energy and mass, they're really the same thing, okay? And so when you say the number of ways to distribute energy in a system, you really are talking about the number of ways to distribute particles in a system. So if I go back to this example of H2 versus 2 that transitions to 2 H dots, we can create a universe that will describe this situation. Let's say the universe has 9 spots. It has 9 spots in both cases, right? Because we're in the same universe for products and reactants. But what's the rule about H2? This molecule is clearly bound together. The hydrogens have to be next to each other. And so if I'm going to draw a picture of the 2 hydrogens bound together, then the rule is they have to be in the box, 2 boxes adjacent to each other. So that means they could have been like that, they could be like that, they could be like this. That's certainly okay. They can be down here at the bottom. And so what you see is there's a limited number of ways that you can combine the 2 H2s and so that they're in adjacent boxes. That's the limitation of having a bond between 2 atoms, is that they have to be next to each other. So the number of ways to distribute energy, the number of degrees of freedom for H2 is going to be less than the number of degrees of freedom for H dot, because once I have H dot, I no longer have the constraint of them having to be in the same box. I can have them in any box as long as they're not occupying the same box. So all of a sudden, what you see is that I have every single possibility that was the same as the H2, but now I have added other possibilities, the ones where they're not in the same, where they're not in adjacent boxes. So at the end of the day, the sort of the moral of this story, the take-home message, as it were, is that if you have a situation that where you have one particle, even though it's 2 atoms bound together, it's considered one particle, and you take those the one particle, and they become 2 particles, this is a situation where entropy goes up. So entropy is symbolized by S. If we're talking about a change in entropy, then we do mean entropy final minus entropy initial. If we have a situation like we described, where the entropy in the final state is larger, so that means it's higher, see if I can do it right this time, then the initial state, which is lower, then you get a positive number. And the vice versa would be true. And so this is going to be the primary way that we investigate enthalpy in this course. So we could say something like this. I've got alkene plus HCl, and I create a chloroalkane. How is the entropy change in this case? I've got delta S, and the final position is 1 particle. So it has more constraints. It's lower energy. It's smaller. It's a low number minus a high number in the reactants, because I've got 2 particles. So in this case, delta S is negative. And so this is what entropy is all about. And that's how we're going to do it. We're going to just look at the number of particles. Generally, if there's more particles, then the change in entropy was positive. If there's less particles, then the change in entropy is negative. Now, there is one other situation that we need to look at. We need to look at the situation like this. Okay. What if I go from a ring to a chain? Now, I've got some other things that are going on here besides this. Let's add a double bond so that I'm talking about the same molecule. In this case, I've got something that is a ring going to a free chain. How does that entropy change? Well, if I have a ring, it is more constrained. So it has lower entropy than a chain. The chain has free rotation around all of its bonds. A ring does not have free rotation here. Because if it did have free rotation, then what would happen is the bonds would break. So in order to leave the ring the way it is in the state of being a ring, we can't just allow the bonds to freely rotate about each other. So that means it's more constrained than the chain, where the bonds do actually have free rotation around any of those bonds. And so that means we get to this situation where we have low entropy versus high entropy. And in this case, we got a small number minus a high number. So I did it again. The final state has higher entropy than the initial state, lower entropy. The entropy in this case goes up. So this is the other way that we'll deal with entropy. So way number one, count particles. More particles means higher entropy. Second way we're going to do it is rings versus chains. Rings have low entropy, chains have high entropy. And that's how we're going to decide whether or not the change in entropy is positive or negative. Okay, so in class, I said to you that it can be shown. And what I said was, it can be shown means, in a word, we're not going to show you. So I'm not going to show you, but this is what I can show you. But this is what I can tell you. So the first thing we want to do is deal with entropy and what it means. There's two types of entropy when we consider it. Up to this point, we've really been considering the change in entropy of the system. We were looking at whether or not it was a chain or a ring, or another way we were looking at it was whether or not it was a number of particles or more or less number of particles. So we were able to figure this out. We can figure this out. Okay. Now, there's this other entropy, right? So when we talk about chemistry, we talk about thermodynamics. There's two things that we think about. We think about the system and we think about the surroundings. Now, the system is always the molecules in the reaction that we're talking about. The surroundings is everything else in the universe. Oops. All right. Now, we can figure out what the delta H of the system is, but we really can't what this is just by inspection. We can't really tell what this is by inspection. And so this is where that phrase, it can be shown, comes in at. What I'm saying is, it can be shown that the change of enthalpy in the surroundings is equal to a term that has to do with the change in entropy, or excuse me, let me say this again. The change in entropy of the surroundings is equal to a term, and that term has to do with the change in enthalpy of the system. So this is what we know. We know that the change in entropy of the surroundings is equal to negative delta H of the system divided by the T. And T, of course, in this case would be Kelvin. All right, so why does that matter? This is why it matters. If I want to know whether a process is spontaneous or not, the change in entropy of the universe must be positive. In other words, if the process just happens naturally, automatically, at a given condition, the change in entropy of the universe has to be positive. All right. And so what that means is, now I'm going to create some space. All right. This is what that means. Delta S of the universe equals the change in entropy of the system plus the change in entropy of the surroundings. When this value is positive, the process is spontaneous. When this value is negative, the process is non-spontaneous. And at the end of the day, what we're trying to do is figure out whether or not a process is spontaneous or not. And so we've already told you that the change in entropy of the surroundings is equal to a term that has to do with the enthalpy of the system. And so now we have a way to discuss the change in entropy of the universe in terms of things that only involve the system. Because I can replace this term with this term. And so that's what I'm going to do. I'm going to say delta S of the universe equals delta S of the system minus delta H of the system. Now all I have in here is the system divided by T. Now I'm just going to do a little bit of algebra. Now that I've got all this stuff written down, I'm going to delete it. And so what I'm going to do is I'm going to do just a little bit of algebra. And in this algebra, I'm going to multiply everything by T, right? So I just want to get T out of the denominator, out of the denominator of delta H. If I multiply everything by T, then I get T out of the denominator. So I have to do what I do to one side, I have to do to both sides. So I'll have T delta S universe equals T delta S system minus delta H of the system. Now, that's great. So I got rid of delta, I got T out, I got rid of T in the numerator. I've got everything in terms of the system. And now I know that when this term is positive, the process is spontaneous. Now, the problem is that I need T delta S of the universe is a little bit of a cumbersome thing. And so what I'm going to do is I'm going to multiply everything by -1 just to rewrite that. So I'm going to take -1 there. I'm going to multiply it by -1 here. And then I'm going to multiply it by -1 there. Now I have a new equation. And so I'm just going to do a little bit of rearranging. T delta S universe equals delta H system minus T delta S system. And so now I've got an equation that really does sort of tell me what happens with a reaction, whether it's spontaneous or non-spontaneous, as long as I know one of two things. As long as I know the delta H of the system, and as long as I know the delta S of the surroundings. I don't really need to know the temperature because the temperature is always positive, right? Because we're on the Kelvin scale. And so the only thing that I want to do then is to replace this with a new term. I want to replace the entirety of delta T delta S, negative T delta S of the universe. I'm just going to replace it with delta G. Okay. So now I have the formula delta G equals delta H minus T delta S. And I've gotten rid of the subscript system because now I really am talking about the change in the change in free energy of the system, right? If the free energy change of the system is equal to delta H minus delta H of the system minus T delta S of the system, then I really know whether or not the process is spontaneous. Well, let's just examine real quick. What if delta G is positive? What does that mean? That means that this term, negative T delta S of the universe, is what? It has that this term has to be positive. In order for this term to be positive, delta S of the universe has to be, negative, right? Because the negative times a negative, that equals the positive. If I want delta, so that means that in order for the reaction to be spontaneous, delta S has to be positive. So what does that mean about delta G? It has to be negative. Because if delta G is negative, then that means negative T times delta S. And if delta S is positive, then a positive number times a number that's positive times -1 is always negative. So in this case, delta G being negative means the reaction is spontaneous. And in this case, it means it's non-spontaneous. Okay. Now we're there. All right. So this is the last little piece. Now that we've got that all developed, we figure out where delta G comes from. Now we want to use delta G. So what I want to redo is I want to rewrite that formula. Delta G equals delta H minus T delta S. And remember that we're always talking about the system here, right? This is the free energy change of the system. And now from now on, when we look at energy graphs, we're looking at free energy changes so that I can tell you that if the reaction is like this, delta G is going to be negative, delta G final minus delta G initial, free energy change is negative, a low number minus a high number. This is exergonic. This reaction is spontaneous. And if I take a look at delta G is positive, the opposite situation, this is endogonic. This is non-spontaneous. Okay. So why does this matter? This is why it matters. At the beginning of the day, what we did is we figured out a way to figure out how delta H of the system looks. Now that we know how delta H of the system looks, we can combine that with our method of figuring out what delta S of the system is. And so what I want to do is build this chart, right? Build a chart that says, all right, what is delta G going to be under these scenarios? We have some scenarios here. We have the scenario where delta H is negative, and if delta H is negative, delta S can be positive or negative. We have the scenario where delta H is positive, and under this scenario, delta S can be positive or it can be negative as well. So then how does that work out? All right, let's take a look at the first situation. If delta H is negative, this value is negative, then I subtract it from a positive number times a positive number, or excuse me, a negative number. I multiply it, delta H minus T delta S. So if I take a positive number and multiply it by a positive temperature and then subtract that from a negative number, right? So I have a positive number that I'm subtracting from a negative number, I always get a negative value. So the same would be true if I would have a similar situation if delta H is positive, right? If delta H is positive and I have a delta S that's negative, then I'm always adding, so negative times a negative equals a positive number. And if I have that positive number, I'm always adding them two together. So in this case, it's always positive. So in these two situations where delta H is negative and delta S is positive, delta G is always negative. It's always spontaneous. Conversely, when delta H is positive and delta S is negative, it's always non-spontaneous. Delta G is positive. Now, it can be either or in the other two situations, where delta H is negative and delta S is negative, and delta H is positive and delta S is positive. Well, what does it depend on then? How do I decide whether or not the reaction is spontaneous? Well, it just depends on T. It depends on temperature. Okay, well, we want delta G to be not positive, we want it to be negative in the situations where the reaction is spontaneous. So how do we do that? All right, so in the first situation, delta H is negative. But when I multiply when I subtract a negative number from a positive, if I have delta H, so delta G equals a negative number minus a negative number, then this actually becomes positive, and I have delta G equals a negative or a positive value, and it really depends on how big this second term is. Well, in this case, we know that delta H and delta S are essentially constant values. What determines the size of this term is temperature, right? The bigger the temperature, the bigger the positive term. The bigger the positive term, the more positive delta G is. So in this case, when delta H is negative, how do we get the reaction to be spontaneous? Well, we need that term that's going to be positive to be as low as possible, to be as small as possible. So we need low temperature. Okay, so let's take a look at the situation when delta G, what happens to delta G if this is positive, delta H is positive, and we subtract it from a positive number? Well, in order for delta G to end up being negative, this number has to be large, right? Because if we're subtracting a positive number from a positive number, the only way to get a negative result is from the number on the right to be bigger than the number on the left. So when does this happen? It's negative at high temperature. So to sort of wrap it all up, the two situations in the middle definitely depend on temperature. In the first case, we would need low temperature to make delta G negative. And in the second case, we need high temperature to make delta G negative. So is delta G positive or negative? Well, it depends. What does it depend on? It depends on T. In which case does it needs high temperature, in which case needs low temperature in order to make the reaction spontaneous. And so let's get one example and then we'll cut it out and it'll be the end of the video. So let's go back to something like this. All right, so now we have a way to sort out what delta H is. Remember how we said delta H, we could figure it out with sigma bonds and pi bonds. On the right-hand side, we only have one pi bond. On the left-hand side, we have 3 pi bonds. So the reactants are higher energy than the products. The reactants are higher energy than the products because there's more high energy bonds on the reactant side. So in this case, we know that delta H is equal to a negative value. Now, if I think about it in terms of enthalpy, it's just the opposite situation. I've got an enthalpy that is increasing or decreasing, right? So I went from 2 particles to 1 particle. In this case, if I take a look at entropy, there's more entropy in the reactants than there are in the products, because there's more reactants than there are products. So delta S in this case is negative. So now if I go back to delta G, which is delta H minus T delta S, then this is what I end up with. Equals delta H is a negative number minus temperature times a negative number. So what is delta G going to be? Well, it depends. What does it depend on? It depends on the temperature. It depends on the temperature. What does this term end up being? Well, it ends up being a positive term. Negative times a negative is a positive. So do we want this term to be low or high? Well, we want this term to be small. If the term is small, then delta G will be negative. So in this reaction, is delta G positive or negative? Well, it depends. What does it depend on? It depends on T. And under what conditions will the reaction be spontaneous? It'll be spontaneous when this term is small. So that means low temperature. All right, this is it. This is what it's going to look like. This is what it's going to look like when we do a Zoom class. The only thing that's going to be different is you guys are going to be there. You're going to be able to virtually raise your hand. We'll be able to stop, ask questions. And once I get through a small section like this, we'll stop and do some problems. So this is about as long as that I'd want to take it before we did an example. So I'm going to post this on Blackboard, let you look at it, have a recap of the first part of chapter 6. That way it'll get you going so that you are ready to go for the synchronous sessions that are going to start not next week, not on the week of the 23rd, but on the week of the 30th when we go back to regular classes, but online. So if you have any questions, send me an email and we'll go from there. Okay, guys, see you on the 30th or see you on the 31st. Normal class time, 9:05.